Hi grade 11s, I'm back again with another lesson. As you can see, we'll be continue with Euclidean Geometry and we'll be looking at lesson number 2, and the focus for today is going to be examinable proofs. Just to recall what we've done in lesson 1, we looked at the introduction of Euclidean Geometry by mainly focusing on revision of grade 9, grade 10 Euclidean Geometry, where we were revising your what do you call parallel lines, properties of quadrilaterals, and we introduced the theorems for grade 11, and we look at a circle and all the terminologies like your chord, your tangent, your secant, just so that you can get to your mood and you can get the foundation of what Euclidean Geometry for grade 11 is all about. So without wasting time, we're gonna move into another exciting topic, which is examinable proofs. Okay, so basically on this lesson I'll be going through the 4 examinable proofs that we're gonna get in your examination, and just for you to understand how to prove them using first principle. Okay, if we can recall from the previous lesson, I mentioned that this a document called an examination guideline, and it's very important for you to get this document, as is the one that is going to give you a guideline in terms of how and what you need to prepare for your examinations. And I also advise that you need to make sure that you get this guideline for all your subjects, because it's very important. So as you can see, and I would like us to recap quickly. If I can get a pen. So I mentioned under number 5, this I took it out from the examination guideline, so this is coming from there. Okay, so the focus for today is going to be on these 4 theorems, examinable proofs. So we've got a couple of examinable theorems. We've got a couple of theorems that we need to look at for your grade 11 syllabus, but in terms of knowing their definition and knowing how to apply them when you're solving geometric riders. But most importantly, these 4, you need to make sure that you are able to if I can scroll up so that you can see. These 4, you must be able to solve them using first principle. Basically, not applying the theorems, but being able to prove them, to show how you can determine the proofs while you are given the sketch. Okay, we will get to that in the next slide. But as you can recall, that the first theorem that is examinable is the one that says a line drawn from the center of the circle perpendicular to the chord bisect the chord. Okay. The second one, it says the angle subtended by an arc at the center of the circle is double or twice the size of the angle subtended by the very same arc at the circle. Okay. Number 3, it says the opposite angles of a cyclic quadrilateral are supplementary. And lastly, the one that we're going to look at is a theorem that says the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternating segment. Okay, so I'm going through these theorems, actually defining them, but then on the next slide we're gonna go through each one of them and being able to see how we what's the word? We derive these theorems. Okay, because basically what is given here, we can actually derive it and have a formula for it and be able to prove that indeed this theorem it can be applied and it can be determined using first principle. Okay, so another advice, if you're joining these lessons for the first time, I will encourage you to look at the first lesson where I went into more details and so that you can understand what do you mean by a chord, what do you mean by subtended arc angle, what do you mean by cyclic quadrilateral, what is a tangent, and so forth and so forth. Okay, Now let's look at the first theorem. Okay, so here we will be looking at the theorem that says the line drawn from the center of the circle perpendicular to the chord bisect the chord. Okay, so yes, I've written here that it's theorem number 1, but the numbers are not really important. In some of the books you can have this as theorem number 1A and then it's theorem number 1B. So it doesn't really matter if it's theorem number 10 or number 100. What is important is that you need to know which theorems are examinable. Okay, so if you look at the sketch, and then I also on the first lesson highlighted the importance of the reasoning. That one of the difficult parts about Euclidean geometry is that for every statement that you write, you need to give a reason. And throughout my experience of teaching and tutoring this topic, this chapter, I've learned that a lot of learners, they know, they can see that a certain angle is equal to another angle, but they can't prove or they can't use the correct reasoning for that, and for that they become penalized and continue to say that this chapter is difficult. Okay, but I will take you through all the steps and I make sure that I highlight all the tips and the tricks of this Euclidean geometry. By the way, this is my favorite topic, so I hope it's going to be an exciting journey. Okay, so if you look at this sketch here, it says if, okay, you can see that we've got a circle there with a chord AB, and then we've got a center O. It says that if OM, so if OM, so basically M must be somewhere here. If OM is perpendicular to AB, then AM is equals to MB. That is this summarized in a form of a diagram. So this theorem is telling us that if there's a line that is drawn from the center of the circle and that line is perpendicular to the chord, then there's no other way. That line is going to divide your chord into two equal parts. So it's going to divide your chord into two equal parts. In this case, it would be AM and AM, which will be equals to AMB. Okay, so you'll be given a question that says you need to prove. You'll be given a sketch like this, and you'll be asked to prove a theorem that says the line drawn from the center of the circle perpendicular to the chord bisects the chord. Now there are certain steps that you need to follow, and you can see I've already highlighted 2 of them here, and then we'll go to your construction and then actually come to a proof that is going to tell us that indeed this line, this VT is equals to TW, which is the main priority for this proof. Okay, so let me get another pen so that we can see how we do the proof. Okay, so the main focus for today is all about proving. Okay, so you'll be given, as you can see, it says given chord VW with radius from center O perpendicular passing at T. So basically this is what is given on your sketch. Nothing fancy and nothing to worry about. That is what is given. RTP means required to prove. What are we required to prove? We are required to prove that VT is equals to TW. Okay? That's RTP. Now we're going to get to a very important step, which is construction. So in some construction, I want you to listen to me very carefully. I'm not going to write anything here. We're going to say construction. We're going to join O to W. That is the construction. So you can write there when you're making your notes, join O to V and O to W. That's the construction that we're going to make. Okay? Now, so we are done with the construction. Now you will realize that now we've created 2 triangles here. We've created triangle OVT and then OTW. Alright? Okay, so we're gonna use what we call, the knowledge of congruency. So theorem number 1, it needs you to use congruency, which is a topic that you've covered in your grade 9 and grade 10. Okay, and then as you can see, we've got a 90-degree angle here, so our focus will be RHS, right hypotenuse side. Okay, now this is what we're going to do. We're going to say in triangle OVT and triangle OT. What do we know about this triangle? We know that this side is equal to this side. So what do we know? We know that OV is equals to OW. Now this, if you don't mention the reason, this is not going to be marked. So you need to give a reason. Why are we saying OV is equal to OW? Because they are what you call radius. So we're going to say radii. So it's two of them, radius, radii. Okay? Very important to know what a radius. So a radius is a line that is drawn from the center of a circle to the circumference of the circle. Again, if you're still having issues with the definition, make sure that you catch up on my first lesson. Okay? Now, the second thing that we're going to say is that so angle OTV, so angle OT angle V is equals to OTW. So you can see here the T's got that angle on top. What do we know about this? This is given. This was given to us because they mentioned here that it's perpendicular. So we know that this angle here basically is 90 degrees. Okay. Lastly, what do we know? We can see that, oh, okay, in triangle OVT, we've got side. So this is number 1, number 2, and then this is number 3. We can see that, okay, what do you call, OT, this side is actually common on both sides. So it's common on this triangle, and it's common on this triangle as well. So OT is equals to OT. Then the reason there, you can say it's common. It's a common side. Okay, so now that we've determined the three properties of this congruency of the two congruent triangles, we can conclude and say therefore triangle OVT is congruent to triangle OTW. And also you must give a reason. The reason is what? Right hypotenuse side. Okay, now that we've determined that these two triangles are congruent, we can say therefore VT is equals to TW. And then we have indeed proved that indeed the line drawn from the center of the circle divides the chord into two equal parts if that line is perpendicular. Okay, so we were required to prove that VT is equals to TW, and then we have proven that indeed VT is equals to TW. I hope this makes sense. Okay, we will now move over to the second theorem that is examinable, which is theorem number 3 according to my list. And the theorem states as follows. The angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the circumference, okay? And then it is summarized as angle at center is equals to 2 times angle at the circumference, okay? So what the theorem is saying is that if you've got a circle like that, then this, okay, okay, I need to erase that. What the theorem is saying is that this arc here, it subtends an angle at the center. It also subtends the angle at the circumference, okay? But and then what it's saying is that this angle which is at the center is twice the angle at the circumference, okay? Nothing too difficult there. Similarly, if you look at, so we've got diagram 1, diagram 2, and diagram 3. If you look at diagram 1, the arc subtends an angle at the center. The same arc subtends an angle at the circumference, which is twice that one of the, which is twice that one at the center. Similarly, in diagram 3, an arc subtends an angle at the center, which is twice the angle subtended by the very same arc at the circumference. Okay, that is just a summary of this theorem. Now we will do a similar thing. We will go through first principle of this theorem so that we can see if we can apply what is being said here on the when it comes to the definition. to say the angle at center is the angle at the circumference. Okay, so again, we're going to follow the same procedure. We're going to look at what is given. So what is given is what the sketch is it's showing. It's given that O with a center, center O with Q, P, and R on the circumference. Nothing too fancy there. We can see we've got a circle with O at the center, and then we've got 3 points that are on the circumference. Okay. And then in terms of construction, again, and I want you to listen carefully, we're gonna join Q to P and then protrude or prolong to, I will just choose any, what do you call, I've got P, I'll write this as M. Okay, so we join Q to O, but you don't stop there, you prolong to M. So M is just any point in the middle of the circle. It's not at center, it's not at circumference. Okay, and then I will name this my angle 1, angle 2, okay, and I will name this angle O1 and then angle O2. Okay, now we come into the proof. Now, very important, remember our RTP, which is required to prove. We are required to prove that POR is twice PQR. So that is our aim. Okay, so this is how we're gonna go about. I want you to look at this triangle. Oh, I need a different color. Let's look at green. I want you to look at this triangle. It's gonna be messy, but the most important thing is for you to see. I want you to look at this angle and this triangle. So in triangle QOP, we can see that this angle, which is the exterior angle of a triangle, is equal to the sum of the interior opposite angles. Okay, so we can see that O1 is equal to angle P plus angle Q1. What is the reason here? Exterior angle of a triangle. Okay, very important theorem here. Similarly, in triangle, in the other triangle, QOR, we can see that O2 is equals to, so the exterior angle is equals to the sum of the opposite interior angles. It's equals to R plus Q2. Okay, gonna have the same reasoning there. Exterior angle of a triangle. Oh, this pen doesn't look nice, so let me get another pen. Okay, so we've established that after constructing this line here, which joins Q to O and prolongs to M, we discover that we've got a triangle, we've got two triangles here, and then we've got the exterior angles that is outside, which is equal to the sum of the interior opposite angles on both the two triangles. Okay, so now that we've got this and we've got this, we can say therefore angle O1 plus angle O2. So here we are just adding. So we are adding what is on the left hand side, we are adding it to the right hand side, which is equals to P plus Q1. Okay, plus R plus Q2. Okay, nothing too fancy there. So what did we do? We added this, which is on the left hand side, and this, which is on the right hand side. Okay, now we're gonna move over and say, okay, okay, so we're gonna continue and say, but angle P, which is this angle, is equals to angle Q1, which is equals to angle Q1. How do we know this? Because these are base angles of a triangle. So because of the radii. since this is a radius and this is a radius, the angles opposite the radius are equal, okay? And then at the same time, on the right hand side, we can say angle R is equal to angle Q2. What is the reason there? The same reasoning, because of the two radii. The two radius are equal, so or you can continue and say angles opposite equal sides are equal. So that is just a summary of the theorem, or the explanation, to say if you've got two lengths that are equal, the angles that are opposite those equal sides are also equal. So angles opposite equal sides. Okay, so now that we've established that this P is equal to Q1 and R is equal to Q2, I can substitute this into this equation that I've already set for myself. Just want to scroll down so I can have enough space. Okay, so from here I can say O1 plus O2 is equals to, so where I see P, I'm going to substitute Q1. So where I see P, I'm going to substitute Q1. I've got my Q1 that is already there. Plus, where I see R, I'm going to substitute Q2 because they are equal. So where I see R, I'm going to substitute Q2 plus Q2. And then I also had another Q2 here. So what did I do? I wrote my equation the way it is. Where I see P, I substitute Q1, which is here. And then where I saw R, I substitute Q2, which is there. Then the rest remain the same. And then I can continue with my equation and say O1 plus O2, 2. So you will see that I've got 2 times, so 2 times Q1 plus 2 times Q2. So we've got like terms here. Then I'm going to simplify this. I've got a common factor of 2. I'm going to take 2 outside, which is Q1 plus Q2. And if you look at what is Q1 plus Q2, Q1 plus Q2, so Q1 plus Q2 is the same as angle Q, is the same angle Q. So at the end I've got O1 plus O2, okay? But that is not, but we can also see, we can say, this is the color that I don't like. O1 plus O2, what is O1 plus O2? How can I write this angle O1 plus O2? Because angle O1 plus O2 is this angle. So O1 and 2, maybe let me get, seems to be struggling to get an eraser, but anyway, so basically O1 plus O2 is this angle. So this is O1 and this is O2. Apologies for the mess that I've created here. So what is this angle? This angle is the same as POR. So O1 plus 2 is the same as angle POR. Similarly, what is angle Q? Angle Q, if you look at angle Q, is this angle. I can write it as PQR. I can write this as PQR. Therefore, if I go back and substitute, I realize that, okay, where I see O1 plus O2, I can write it as POR, which is what I'm going to do. Therefore, on the left hand side, where I see O1 plus O2, I can write POR, which is equals to that. Similarly, where I see angle Q, I can substitute PQR. I can substitute PQR. Now let's go back and see. But I left something that is very important. There was a 2 here. So there was a 2 there. So I need to put in my 2 there. Okay. Now let's go and look at our required to prove. Our required to prove, which is what we are asked to do. Is it the same as what you got? The answer is yes, because it's 2 times PQR, and this has been proved. Okay. Apologies for all this mess, but this is what Euclidean geometry is all about. You need to be able to have different colors so that you can see which angles are equal to which angle. Okay, I hope this makes sense. Okay, let's move over to the other theorem, the next theorem. Okay, theorem number 6, which says, and it's one of the ones that are examinable, which says the opposite angles of a quadrilateral are supplementary. Okay, the opposite angles, opposite, it means the ones that are facing each other, are supplementary. Okay, and then if we look at the a diagram that shows or that summarizes this theorem, and also in terms of the reasoning says opposite angles of a cyclic quad. Okay, going back to the diagram, it says if AB is a cyclic quadrilateral. What is a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral within a circle whereby the 4 points touches the circumference. Okay, so if ABCD is a cyclic quadrilateral, then the opposite angles, so angle A will be equals to they are not equal, but they are supplementary, which means angle A plus angle C, they add up to 180. Similarly, angle D and angle B, they add up to 180 degrees. Okay, that is just a brief summary of the theorem. Okay, now let's go to the proof, step by step, of how to prove that this theorem is indeed valid. We're gonna look at the 4 steps that we go through. The first one is what is given. We are given that center O. So one thing that is missing here is a center O in the middle. Center O. With O, okay, maybe let me do this. Let me do this. Ah, man. I have to use a different color. So I wanted black, but it's fine. Center. Okay. Center J, K, L, and N on the circumference. So that is what is given. The circle is given there with a center O, J, K, L, M, N on the circumference. Okay. And what are we required to prove? We are required to prove that K plus K equals to 180 degrees. So we are required to prove that angle K and then angle M, when you add them, they add up to 180 degrees. Okay. So in terms of construction, this is what we're going to do. So since they want to look at K and M, we are going to construct J to L. Okay, I'll repeat that. If they want us to prove that K plus M is equals to 180, we construct J to O and O to L. If they wanted us to prove that J is equals to L, we construct K to O and O to M. I hope it makes sense. Okay, so we join this with radius, so that we know that this radius is equal to that radius. Or not that it's going to be important for this proof, but just for you to take note. Okay, now that I've divided this cyclic quad into 2 triangles, I can rename this and say, again, I've got angle O1 and then angle O2. Okay, so we are coming to the proof. I've done with the construction. So what are we going to say? So we will realize that I've got a triangle that is like this. Then I've got a circle there. I've got J. I've got an angle there, and then I've got an L with a K there. So you will realize that this arc, subtended angle at the center, and then the same arc, subtended circumference. So it's taking us back to the previous theorem. So you're going to say angle O2 is equals to 2 times angle K. What is the reason? Angle at center is equals to twice angle at circumference. Okay, I hope we are clear on that one. Okay, what happened to my pen now? So we are done with the first one. I'm gonna draw the second one so that you can see what I'm referring to. So we've got this type of a situation. We've got M there, we've got L there, something like this. Then we've got O2 there. So you realize that here we had 2. So we've got 2 there, we've got 1 there, angle O. We've got J, M, and L. Okay, so again, this is theorem number 2 that we've looked at in the previous slide. which says angle at center is twice the angle at the circumference, because if you look at this triangle, this angle, which is subtended by this arc at the center, is twice the angle subtended by the very same arc at the circumference. Okay, like I said, it's going to get messy, but the most important thing is for you to get a picture of what I'm referring to. So in the other triangle, we can say O1 is equals to 2 times angle M. What is the reason? It's the same reason as angle at center. Just write the summary. The angle at the circumference. Just in a summary there. Okay. Now, moving on, we're gonna say, is that blue? I don't like blue. So we're gonna add the 2. We're gonna say, like we did on the previous one, we're gonna say O1 plus O2 is equals to 2K or 2M plus, doesn't really matter. You see, if you start with M or you start with K, plus 2K. So these are my angles, M and K. So you don't need to write the reason here, we just added the 2. So you added this, it's there, and then you added that, it's there on the right hand side. Okay, this is just basic algebra. Okay, so O1, okay, now I'm going to summarize this. I've got 2 as a common factor. I'm going to say 2 plus 2M, and then I'm going to say, but what is O1 plus O2? What is O1 plus O2? So O1 plus O2, what is that? That is revolution. So it takes us back to your grade 9, grade 10. Angles around a point, they add up to 360. So O1 plus O2 is equals to what? 360. If you add angle O1 plus angle O2, you will get 360. Why are you saying that? You put the reason, revolution. Angles around a point, they add up to 360. So now, what am I going to do? What am I going to do or say? I'm going to say here, where I see, where's my highlighter? I don't know why this highlighter doesn't want to work. I'm going to say, where I see O1 plus O2, I'm going to put 360. Okay? So, where I see O1 plus 2, I'm going to say 360 degrees is equals to, this is still the same. Okay? I write this the same it was. I'm going to say, but I've already summarized it here. So, it's equal to 2 into M plus K. Remembering that these are angles. Then, I'm going to divide on both sides by 2. So, I'm going to have 1 degrees is equals to M plus K. And if we look at this, so this is the end. If we look at this, is the same as what was required. So this has been proven. Okay, very simple, straight to the point. Know your basics, angles around the point, construct, use the angle at center is twice the angle at the circumference, and then you're good to go. Just basic algebra. Okay, hope we are on the same page. We are now going to look at the last theorem that is examinable, the proof that is examinable. And according to my list on this theorem number 10, which says or which states as follows: the angle between a tangent and a chord is equal to the angle in the alternating segment. Very, very important theorem. In most cases, every time you see every time they've given you a tangent, you are likely going to need this theorem, tan-chord theorem. That's the summary of tan-chord theorem. Okay, so let's look at the diagram. Let's also read again the theorem. It says the angle between a tangent and a chord is equal to the angle in the alternating segment. Now, this takes me back to my first lesson where I explained to you what is an alternating segment and what makes a circle to have 2 segments. I mentioned that if you've got a circle and you've got a chord, the chord divides a circle into a minor segment and a major segment. theorem is saying is that if you've got a tangent like that, so the angle between a tangent and a chord, the angle between a tangent and a chord is equal to the angle in the alternating segment. So it must be angle A. Okay, so if CD is a tangent to the circular D, then D1 is equal to angle A. Similarly, on the other side, the angle between a tangent and a chord is equal to the angle in the alternating segment. Therefore, C2 will be equal to B. Very, very important. Okay. Now let's look at the theorem and the step by step. Okay. Now again, we need to look at what is given to us. So this is just a bonus. We've got a circle with a center O, we can see, with H, G, and T on the circumference, and TP being a tangent. So that is given. Nothing too fancy there. Now RTP, what are we required to prove? How are we going to prove this theorem? Or what is it that we need to prove for this theorem? We need to prove that PTH, basically this angle is equal to angle G. That is what you were required to prove. Now we're going to look at the construction. What is the construction? So construction, I'm going to say, draw diameter. I'll put this as what? I'll put this as M. So I'm going to draw diameter MT. So if it's a diameter, it must pass through. Draw diameter MT passing through O and join G to M. So that is my construction. Listen carefully. Draw diameter MT, which is passing through O, and join G to M. Okay, then I'm going to name this my angle 1, and then angle 2. Going to name this angle 1 and angle 2. Okay, nothing too difficult there. Okay, now I'm coming to the proof. How are we gonna get here? So we're gonna say, okay, there's a theorem that says if you've got a circle and we've got a diameter, the diameter subtend an angle of 90 degrees. Okay, so the diameter subtend an angle of 90 degrees. If you look at this, we've got a diameter there. We've got a triangle there, and this is 90 degrees because MT is a diameter. So what do we know? We know that angle G1, which is this one, plus angle G2, which is this one. So angle G1 plus 2, which is the whole of angle G, is equals to 90 degrees. That is what we know. What do you call this? The reasoning. It says angles in a semicircle. That is the short version. In a semicircle. Again, if you don't know this reasoning, make sure that you catch up my first lesson where I explain the theorems, the reasoning, and where to get those reasoning from your examination guideline. Okay, so angle G1 plus G2 is equal to 90 degrees. Nothing too fancy there. Again, another theorem that we need to apply here is that if you've got a center there, and then we've got a line that is perpendicular to the tangent, then this angle is 90 degrees. Okay? The theorem says we've got a tangent is perpendicular to your radius. Okay? So we're going to say T1, which is this, plus T2, which is that, is equals to 90 degrees. What is the reason? Radius is perpendicular to tangent. How do we know that this is a radius? Because during my construction, I constructed a diameter, and a diameter is made out of 2 radii. So it means this OT is a radius. Okay. So now that this is equal to 90 degrees and this is equal to 90 degrees, it means G1 plus G2 is equal to T1 plus T2. Okay. So we're going to the therefore G1 plus G2 is equals to T1 plus T4. Okay, there's no need for a reasoning. This is just algebra. This, if this is equals to that and this is equals to that, it means the two are equal. Okay, now I'm going to say but something very important. I want you to look at this. We call it the bow tie theorem. If you've got something like that, then this angle will be equal to that angle. So it means angle T1 is equal to angle G1, but angle T1 is equal to angle G1. Why are we saying that? It's the bow tie theorem, but there's no reasoning that says a bow tie theorem. We call this angles in the same segment. Same segment angles. Same segment. Okay, let me write this. Yeah, this is a very bad color, but we're almost done. So we call it this angles in same segment. Okay, so what does it mean? It means from this equation where I see T1, where I see T1 here, I can substitute G1. Simple as that. So I had G1 plus plus G2 is equals to, where I see T1, I can substitute G1. So I replace this T1 with, I take another pen. I can substitute, man. Why is this? Okay. I can substitute this G1 and then go back to my previous color plus T4. So what did I do? I took this equation that I had where I see T1, I substitute D1 because I already proven that G1 and T1 are equals because they're angles in the same segment. Okay, now I'm going to simplify and then you will see that this G1 will cancel this D1, then I'll be left with G2 is equals to T4. Okay, I'm gonna scroll down so that I can have enough space. Okay. Let's scroll down so that I can have enough space. Now the question is, what is this G4? I mean, what is this G2? If you look at G2, okay, something doesn't know why this thing. You are shouting there and say, wait, we got a mistake there. Where are you getting the 4? So this must be T2, not 4. We don't have a T4. There must be a T2. Must be a T2. So G2 is equal to T2. Okay? But now, this T2, I can write it as, so this T2, which is here, I can write it as PTH. So this is the same as PTH. And then this 2 is the same as, can write it as G without a construction. Then my conclusion can be, therefore, PTH, which is T2, PTH, which is my G2, is the same angle as angle G. And then if you look at this, it's the same as that, and this has been proven. Okay. Nothing too difficult there, grade 11s and grade 12s. I know you are most probably catching up to revise. This is just basic proofs of examinable theorems. I can guarantee you in your test you're going to get one of these, either theorem number 1, theorem number 3, theorem number 6, or theorem number 10. Okay, so this way you need to collect the marks. In most cases this is about 6 to 7 marks. So according to my understanding, or how can I put this? For me, these examinable proofs should be money in the bank. there should be free marks. There's no way that you cannot get this right. You just need to make sure that you practice, you know the steps, you know from what is given, what is required to prove, and how to construct, and how to get to the required to prove using certain steps. Practice, 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 and you'll get this right. It's going to get more exciting on the next lesson, where I will now be going into more details, looking at the theorems and the type of scenarios that you're going to get. You will see here I was mentioning angles in the same segment. You're going to get to more details, the types of angles in the same segment, angles in the semicircle, and we're going to look at the angles in the same segment. We're going to go into more details. Remember in the last lesson I mentioned that we've got three groups of theorems. We've got theorems that falls within centers and circle. We've got theorems that are from the cyclic quadrilaterals, and we've got theorems that are from the family of tangents. So in the next lesson, we'll be exploring those theorems, enhancing our knowledge on these theorems, because in the next upcoming lessons, I'll be doing tutorials where we will also be solving geometric riders. But before we can get to that, we need to make sure that we know all the basics, and that will complete the end of this lesson. Continue to practice and take good care of yourself. I thank you.